You're right. Exactly.
Feeling it.
Are you dead inside? I'm tired. I don't want to do it. I just thank you for noticing. It does. It really.
I really appreciate it.
Thank you. Thank you. Okay. I really appreciate that. Thank
Seven. Oh. Okay, time to get started. I think I've got everybody checked off on attendance, by the way. Okay. So we were almost done talking about vector line integrals last time, just not quite. Just one last thing I wanted to do, really, and that is to, sorry, I meant vector surface integrals. So what I want to do is point out how much vector surface integrals have to do with vector line integrals. They have a tremendous amount in common. Now, at a glance, you wouldn't think so, because after all, vector line integrals compute work, physical quantity, sure, right? But that's it is what it is. But a vector surface integral doesn't compute work, nor anything like it. Vector surface integrals compute flux, right? It computes the quantity of fluid flowing through a surface per unit time. One way to think about it. So the fact that those two physical quantities are computed by different mathematical constructions that have something to do with each other is actually pretty surprising. So I think this is worth spending a little time on and elaborating. And ultimately, by the way, underneath all of this, I want you to be thinking about, where this all comes from, which, again, sadly, is one of these things that's beyond the scope of this course. But the reason that these have so much in common is that they're both ultimately examples of the same things. Vector line integrals are examples of what's called integral of differential forms. Vector surface integrals are different examples of integrals of differential forms. So they're really ultimately, pretty accurately, they are the same thing. They're just different examples of this same thing. Okay, all right, so let's see the analogies that we actually can see. We start off, for example, with a curve, an oriented curve, and we orient the curve by way of a unit tangent vector. With vector surface integrals, we start off with a surface. We start off with an oriented surface, and we orient it by a unit normal vector. Okay, so in both cases, we start off with an oriented thing. All right. How do we compute whatever it is that we're computing here? Well, we parameterize. bad color choice, sorry. We parameterize in both cases. And in both cases, there is a computation that we do involving derivatives to compute, well, in the case of a vector line integral, another tangent vector. And in the case of a vector surface integral, another normal vector. Right? And now let's start looking at how these things play out in the equations. You may recognize all of these equations that I have written down here. These are equations involving the participants in the discussion of vector line integrals. And then down here, equations relating the participants in vector surface integral discussions. Well, let's color code. I think it pops off the page better if you do it like this. But unit tangent vector, unit normal vector. Let's see here then, the velocity vector, the normal, the parameterized normal vector. You see how the colors lay out the same. Okay. Now, again, in both cases, there is a single vector that describes what I like to call everything you need to know about the corresponding, oh, I forgot my mask, I'm sorry. I've got to remember this better. Oh, okay. In both cases, there is a single vector that tells you everything you need to know about your corresponding piece of the domain. So when you're talking about vector line integrals, there's this dx vector thing, right? That dx vector, its direction is the orientation direction. Its magnitude is the size. Well, likewise with surfaces, there's the ds vector. Its direction is the orientation, and its magnitude is the size of that piece of the domain. And notice where they show up in these calculations. And then, of course, now let's talk about the sizes themselves. The size of the piece of curve is d little s. The size of the piece of surface, d capital S. And you see how these things lay out exactly the same, down to even, the role that the parameter differentials play. Right? The analogies are unbelievable. When you lay them out like this right next to each other and compare and contrast, it's, oh my God, it's exactly the same thing. Everybody see what I'm talking about here? So why is this? Oh, and let me, before I go on to why we care about this, the analogy continues if you look at the different forms that these integrals take. And I'm not going to go through and do all the color coding because it would take too long, but everything fits. So these are accumulating quantities. There's the compact version where you use the curve and surface differentials. Right? The vector differentials. There's the parameterized versions. And then there's the what you might call the scalar-like versions, which again are computed in terms of components. So strong analogy just between the different choices that you have between the two different kinds of integrals. Okay. All right, so why should we care about this? Why should you be interested in this? Well, for one thing, this is a fundamental truth of reality, and that's kind of what math is about. So if only as a cultural point, realizing that these two seemingly different objects are, in fact, both examples of the same thing, that's just, that's sophisticated, rarefied information to know. And that's a good, if only for that reason. The next thing I'll point out is just the fact that their analogies are here is helpful as a memory tool, really, because, well, you now are no longer having to memorize two separate sets of equations, really. You're really memorizing one pattern and two versions. Right, so that's, I don't want to say it cuts your memory in half, it cuts your memory requirement in half, but it definitely is a good memory tool. It's easier to remember things when there is a pattern to them. And this is a very strong pattern for that purpose. And the last observation I'm going to make is that, when there's a pattern, that suggests that you can use what you understand about one side to understand the other. So, for example, a lot of people get confused as to, wait a minute, what's the deal with the ds vector? How do I think about it? What does it do? Where does it come from? What does it relate to? By way of this analogy, you can note that the ds vector, it's just the surface integral version of the dx vector. And the dx vector is a lot easier to understand. It's a lot easier to see. In fact, we even see the dx vector kind of before we even really think about the, maybe t or v vectors, arguably. It's very, very naturally. It's the come on, it's going along the little piece of curve. It's the displacement vector, right? So how do we understand the ds vector? Well, it plays, sure, it's geometrically different, of course, but it plays a role. It fits in with the computations. It relates to other things, exactly an analogy with the dx vector that you may already understand better. So I think that's a good learning tool. Patterns can help you, use existing understanding to turn that into a new understanding. Yeah.
So the little n vector is a unit vector, right?
Yep.
So what's the length of the ds vector?
The length of the ds, let's see, in fact, I've got that right here. The length of the ds vector is the area of that little piece of surface, in exactly the same way that the length of the dx vector is the length of that little piece of curve. I think I said length, I meant area. Yeah, but size. Yeah. So that's a great example, live action, great example of, if you need to understand, one thing, think about, go to the analogy, go to the other side, ask the exact analogous question, and the answer to the analogous question very often is the answer to the question you were looking for. Yeah. Okay, great. Okay, so I think that's interesting. There's a lot to digest here, and I encourage you to spend some time on it. Stare at this, look at the analogies, kind of check it all in your mind, make sure everything fits together. And I think there's a lot of benefit that can be had from that. So I hope you'll spend some time on that. Okay, and now moving to section 7.3. This is another section that's a long one. It's another section that arguably should be 2 sections. In fact, you can even see it in the title. This is Stokes's theorem and also Gauss's theorem. And they're both pretty substantial theorems that are worthy of significant discussion. So anyway, I think it's a lot to squeeze into one section. I would have made it 2, but whatever. Most books make it 2. Doesn't really matter. It's the same number of pages. So let's talk first about Gauss's theorem. By the way, the book does Stokes's theorem first, and there's a point of view there, pros and cons. I'm going to do Gauss's theorem first. I think it's easier to relate to, and most books do Gauss's theorem first. So I'm gonna do it that way. So you'll have to skip over some pages to get to it. Okay, so Gauss's theorem. Honestly, a lot like Green's theorem. You're going to notice in today's lecture, I'm going to be flipping back and forth between the chapter 6 notes and the chapter 7 notes, because there are so many analogies between these new theorems and this old Green's theorem that we already have seen a lot about. Okay, so in particular, in both cases, we're going to be talking about a region and its boundary. So we had to define exactly what we meant by boundary. Remember, when we started with Green's theorem, the word boundary becomes a loaded word. Boundary now specifically means oriented in a very specific way. It's wrapped up inside of that word boundary. When you say boundary of a 2-dimensional region, that's not a curve, that's an oriented curve, specifically oriented a certain way. Okay, all right, so we got to do the same thing now with solids. Here's the rule. The rule is, if you have a solid, now you'll notice that the solid that I drew here is a hollow solid. I mean, it's got mass around, but there's also a big sort of air gap, air hole in there. So it's like a racquetball or something. So there's my solid. When we say boundary means partly exactly what you would expect, and then partly the loaded, the new, notion of orientation, in the sense that it's exactly what you mean. Yeah, it's the surface. You know what I mean by this. It's the edge. It's the border between solid and not solid, right? You know what I mean by boundary, right? But again, now this word is now loaded. Boundary means oriented in a certain way, and the orientation, here's the rule: oriented away from the solid, oriented into the not solid region, right? In the sense that the boundary is it's the border between solid and not solid. The orientation always points away from the solid and into the not solid. So now this is another one of these things that's very often sort of mistaken. It's all very often misrepresented. It's very often told that the boundary is always oriented outward. And you see from this example here, it's not, right? I mean, on the outside part of the boundary, yes, away from the solid means outward. But if there is an interior piece of boundary, it is not outward. It is, in that case, inward. So again, rather than trying to memorize a list of rules, well, in these various cases, then it's inward, and these other various cases, it's outward, and it's much easier just to remember very simply away from the solid. And that's what's always accurate. Everybody good? Questions? Feel free. Okay. All righty. Okay. Next thing we did with Green's theorem. We talked about this idea of accumulation. Now, I sort of introduced the idea of accumulation here. I'm not going to reintroduce the concept of accumulation. It means, we've talked about what it means a lot, but it's, objects, quantities, whatever they may be, physical or otherwise, that the whole is the sum of the parts, right? And so for some things like mass, yeah, mass, the whole is the sum of the parts. But for other things like perimeter, the perimeter of the whole is not the same as the sum of the perimeters of the parts. It just doesn't work, right? So there's this very specific property that some objects have, some quantities have, some quantities don't. Okay. Anyway, so the as is relevant to Green's theorem, boundary circulation is the accumulating quantity, right? Now, reminder, we did a bunch of stuff with Green's theorem, blah, blah, blah. Then we went on and we tried to relate it to this other thing called boundary flux. And then, you can do some algebra and show that the circulation Green's theorem and the flux Green's theorem are actually connected algebraically. And that's nice and all. But here's the thing. You can also just think of boundary flux itself as an accumulating quantity. And here's that picture that we drew, right? The boundary flux of the whole, the boundary flux of the parts, they add up just like they're supposed to. So boundary flux, this is the alternative version of Green's theorem. Boundary flux is an accumulating quantity. Okay, so with Gauss's theorem, we are again going to be looking at accumulating quantity, and that accumulating quantity is boundary flux. And check out the picture. In fact, you'll notice here that the picture that we have for the accumulation of boundary flux over solids is so reminiscent of the picture that we have here for the accumulation of boundary flux over areas. I mean, it's three-dimensional there, two-dimensional there. Morally the same picture, and morally also this happens for the same reason. This accumulates because of the sort of the cancellation that happens on the shared boundary edge of the two pieces, one oriented that way, one oriented this way. Those cancel. And likewise over here, why does this thing work? Well, because there's a shared boundary face. one oriented that way, one oriented that way, and they cancel. So this new accumulating quantity that we have, boundary flux through the boundary of a solid, it's really just a rehash. It's a ripoff of an idea that we already talked about. It's just a three-dimensional version of this. What do you think? Everybody happy with that? Okay. All right. Hard to hard to draw the sort of, when you have a lot of different pieces, let's go back here just because I have this picture right here showing what happens to boundary circulation when you chop it up to lots and lots and lots of pieces. But the point is, on each shared edge in the middle, you get the exact same cancellation. Let me do that better. The exact same cancellation that you did before. So the same is true here. It's just that if I try to draw a bunch of these little boxes on the inside of the solid, the picture gets far too cluttered to make sense out of. It's just it's too hard. But the point is, if you were to draw such a thing, there would be, oh God, my stylus is really not working right here. There would be shared boundary faces, and it doesn't matter how many of these shared boundary faces you have, they always appear twice, opposite orientations, they cancel. Okay, so the fact that this quantity, boundary flux, accumulates means, again, that it behaves like a stuff. It behaves like, physical, it behaves like mass, kind of. Why is it that if I take a solid and I cut it in half and break it into two solids, why is the original mass of the whole equal to the mass of the two parts? Well, because it's stuff. And because me drawing lines on a piece of paper does not make mass spontaneously disappear or spontaneously be created, right? Physical stuff just doesn't care about lines I draw on a page, right? So flux, this boundary flux stuff, it's kind of behaving in the same way like a stuff. And I encourage thinking of it that way. I encourage thinking of boundary flux, even though it's computed on the boundary. Think of it as a almost kind of physical sort of a thing that resides in the interior of your solid. Yes, it's measured on the boundary, but it actually lives in the interior. It actually is, in some sense, in the interior. And I have some physical examples that are highly supportive of this point of view. We'll get to those in a few minutes. How are we doing? Is everybody with me? Okay. So specifically, I can talk about, it's not just that the boundary flux that I measure there is, somehow in the interior. I can talk about exactly how much of it is in any given little region. You give me a little box, I can tell you how much boundary flux there is, how much of this overall boundary flux, how much of that is happening in one little spot. And with that, I can correspondingly talk about its density. Right, in the same way that looking in a little box, and of course these should be three-dimensional, but the picture makes picture's harder to sort of see. In the same way, I can talk about the mass in a box as being a density times a volume. Density just being stuff per unit size. Right. Well, likewise, I can talk about how much flux there is in a little box. And I can think of that flux as relating to volume and therefore have a corresponding notion of density. It's flux per unit volume instead of mass per unit volume, appropriate to the fact that, we're talking about flux accumulating instead of talking about mass accumulating. It's the same basic idea. Is that cool? Now here's where I'm going to sweep some details under the rug. So how do I compute this flux density? What is this flux density? There's some details there, and I consider those to be nitty gritty and not really not a top priority for me for you to understand as you leave Math 219, right? How to derive the result I'm about to give you it's details, right? Of course, what the result is, what that flux density is extremely important. And this is the formula. And you may recognize this formula. This is something that the book introduced back in chapter 3, sans context, right? And gave the name divergence. And of course, these two notations that you may recall, I hope you all recall. If not, then let me remind you, these two notations for this thing called divergence. Okay, but now I hope you can see, literally what it means. I mean, the reason, aside from some algebra that we're skipping over, the point is this formula is literally telling you how much of this accumulating quantity per unit size. That's why this measures, what they said in chapter 3 is what measures how much the vector field is kind of emerging out, in some sense away from a local region. And you have to talk about, well, there's also the possibility that there's just more going out than there is going in. That's still divergence, and there's all these, it's kind of nebulous, but here, yeah, no, it's literally flux per unit size, and in any form that may take. So that's why this formula is interpreted like they say. Okay, pausing on that. You know what, let me just go ahead and leave this highlighted. So all these, one thing to keep in mind, all of these things that I have circled in blue, they all mean the same thing, right? Del dot, div, divergence. Of course, these look pretty similar. That's not a surprise, right? But this formula and flux density, they all are talking about the same thing. So make sure to be comfortable that you can interchangeably, think about these. Sometimes the theorem that we're in the process of working up to, sometimes it's stated with that, and sometimes it's stated with that, same theorem. And likewise, sometimes it's interpreted as, yeah, well, it's an integral of flux density. Yeah, same thing. Okay. All right. So now, just before we wrap it all up and state the theorem and start doing examples, let me just show you that just like we did with Green's theorem, divergence can literally tell you how much flux is happening in a given place. And I want to flip back over to the Green's theorem section, and I gotta find where I put this. Oh yeah, it was the comparison here. Yeah, right. So y'all remember this discussion here, I hope, where I compare to the fundamental theorem of calculus. I make the innocent, highly believable assertion that while change is measured on the boundary, it actually happens in the interior. And furthermore, not only does it actually happen in the interior, but we can even see in the graph how much is happening there, perhaps compared to there. Right? We have this thing called the derivative. And the derivative is what tells you, yeah, this accumulating quantity of change, where is it? Well, there's more of it there, right? And, not as much there and none happening over here. The derivative is the giveaway of where the change is happening. Well, same with divergence. It's just that divergence is telling you where that flux is happening. So easy little example here. Here's a vector field. It makes a flux through a certain ball, whatever. I don't even know how much flux that is. It creates some sort of a flux. I could very easily address the question of where is that flux, whatever it is, where is that flux coming from? Is it coming more from this point or more from that point? Well, compute divergence. Divergence is the giveaway. And you see that the divergence is bigger at B. And so there is more flux. There's more of the boundary flux that you're measuring, right? More of it is happening here than is happening there. And some is happening at the point A, but not as much. Totally analogous to this observation here from the derivative. Everybody see what I mean? So the intuition that you have, which I know you have excellent intuition for how change adds up over time, and the derivative is literally capturing how much change is happening, right? That intuition that you have for the derivative's role in accumulation of change and the derivative's role in the fundamental theorem of calculus, which is what puts this all together. That's all perfectly analogous to what's going on here with flux and divergence. And ultimately, the big theorem we're about to write down, which is called Gauss's theorem, Gauss's divergence theorem, or sometimes just the divergence theorem. So putting it all together, we have this thing called flux that we talked about last time. Interested in it for various different reasons. It's an accumulating quantity. You can draw the pictures like we did, and interior shared faces cancel and opposite orientations and all that. It's an accumulating quantity, and furthermore, the amount that there is in a given region relates to volume by way of a density. So notice the exact same pattern, right? This is exactly the argument that we made when we were talking about Green's theorem, that there's a quantity we were interested in. Now it was circulation. We observed that it's an accumulating quantity, and then asserted that there was an associated notion of density. Same strategy, different details, different geometry, therefore, different formulas, sure, but the big picture is the same. Okay, so there you go, Gauss's divergence theorem. And again, how you write this, I mean, it's very commonly written like this, as a double integral of a vector, flux of a vector field over a boundary surface is a triple integral of divergence over the interior. It's a very common way to write it. But you can also write it like that. It's also quite common, right? In other words, the thing that we're computing over here, flux, yeah, it has a formula, but it also just has a nice convenient little label. And so, sometimes you want to write it like that. Any combination in some sense that you like of using all of these equivalent representations of divergence. Okay, pausing. Whoops, wrong button. Here we go. What do you think? Got an example ready to go here. Okay. All right, so here we go. We want to compute a flux, it says. Fine. We're given a surface. We're given a vector field, compute the flux. Now, you could straight up parameterize, plug and chug, right? There's the brute force, take a deep breath and plow approach here. I really don't want to do that. And again, I just think it's amusing to contemplate the horrors that would ensue if you were to do that. If you were to parameterize here, let's keep in mind, you're talking about a sphere, and pick your evil. You're either going to be loaded up with trig or you're going to be loaded up with square roots, or worse. The best case scenario is either square roots or trig, and you got to go with the trig. I made that case previous. I think the trig is the best option, and that means that x, y, and z are chock full of trig. Well, then, look, if each one of x, y, and z, if all of these are chock full of trig, then you have a nightmare of a vector field when you pull back through that parameterization. It's just, horrifying. So let's not do that. If we could possibly avoid it, oh my gosh. Everybody see why I don't like doing this brute force? Okay, so let's do this the clever way. I'm gonna come up here to Gauss's theorem. I want to point out, just like I did with Green's theorem, that specifically, and it says right here in the theorem, this theorem does not apply to just any old flux you feel like. This theorem explicitly says right here, only applies if your surface through which you're computing a flux is a boundary. It has to be a boundary. This is not a fine point of formality and rigor either. It has to be a boundary, because the thing that it's the boundary of is going to have to be the domain for this triple integral that you're claiming you want to turn it into, right? If there is no thing whose boundary is your surface, then there is no triple integral at all. You can't, it's not that Gauss's divergence theorem isn't true. It's that there is no Gauss's divergence theorem at all. Right? There is no triple integral to even wonder if it might equal to the flux, right? So this is a big point. A lot of students mess up on this, by the way. You've got to check. I cannot emphasize this enough. You've got to check and make sure that your surface actually is a boundary. All right, yes.
That just means it's like a closed surface.
Yeah, that's right. It means it's a closed surface. Exactly. Yep. Yeah. So let's look at our question down here. Let's address that before we start writing down a bunch of nonsense accidentally. We've got a surface here, and there it is. It's, let's see here, it's the unit sphere. Is the unit sphere a boundary? Yeah, it is. Sphere, right? That sphere is the boundary of the ball that's inside of it. Okay, not quite. There is the issue of orientation. We got to worry about orientations. And you remember this word boundary now means oriented in a very specific way, and this one is oriented the wrong way. So S itself, I mean, here it is. S is this surface oriented that way, and that is not a boundary. However, this surface, oh, I just wanted to hit this surface here, same surface, but oriented the other way, S minus, that is a boundary. Right? S minus is literally the boundary of the unit ball. And let me, again, for color coding purposes, it's that solid region right there, this green ball. So S minus is a boundary. I can apply Gauss's divergence theorem, therefore, to S minus. So problem is, we're not interested in S minus explicitly, we're interested in S. So the first observation that you need to make, I encourage, is to note that the flux we're actually interested in is the negative of the flux through the opposite surface. And then to notice, well, you've already noticed this, but to recognize that opposite surface is a boundary of the solid that you've identified. Everybody see what happened there? Okay. All right. Okay, so that noted. Now, yeah, there's a minus sign that comes from orientation issues, but ignoring that minus sign for the moment, look at this, what I've got. I've got a flux through a boundary. That is exactly what Gauss's divergence theorem is about, flux through a boundary. There it is. The divergence theorem tells me that I can rewrite that as a triple integral of divergence over, of course, the corresponding solid. Y'all may recall, I like to call that the anti-boundary. I think that kind of rolls off the tongue nicely. So here it is, divergence theorem. That flux integral, that boundary flux integral, I'm just rewriting as a triple integral of divergence. There's where I invoke the divergence theorem. Right here. How we doing? By the way, don't forget your minus sign. It is really easy to forget. Y'all have caught me forgetting forgetting to carry over that minus sign. So anyway, it's easy to do, isn't it? Right. So make sure that you don't make that mistake, and you got to make sure to carry that on over. Anyway, there you go. And so now it's just a matter of working out the details. We've got to compute the divergence of this vector field here. There's my vector field. Got to compute its divergence. And so you take various partial derivatives. Remember, we got this formula here for divergence. There you go. So x partial of the first, y partial of the second, z partial of the third. That divergence turns out to be really nice. It's just 3 plus x. And so we have a much simplified problem. Everybody good? Will it always work out this nicely? No, I manufactured one that would be awesome. right? I'm making a pitch here how great Gauss's theorem is. So of course I started with a good one. Gauss's divergence theorem, kind of like Green's theorem, kind of like the fundamental theorem of line integrals. I mean, it turns one question into a different question. So maybe it'll help, maybe it won't. But sometimes it does, and it's surprisingly often it does, by the way. And in physically important examples, it disproportionately does help. So it's a really, really powerful tool. And let's finish up the details on this example here, by the way. So we've got this triple integral remaining to be computed. And the move here, you know, if you look at that integrand 3 plus x, it doesn't have any symmetries. And it's not a constant, and it's arguably, you know, if you were to brute force this, it's you gotta have to spherical coordinate triple integral, right? But look at this slick move. Separate this into 2 separate integrals. This integral is the integral over a constant over a barnyard variety geometric solid that we know the formula for the volume of, and this is 0 by symmetry. So very neat move. Be on the lookout for this. If you have an integrand that itself is not very nice, consider the terms separately. They might be nice in different ways. Okay. What do you think? All righty. So yeah, great theorem. Let's see, are we on to, yeah, okay. So absolutely want to make sure that you know this theorem, but want to make sure that you know the formulas here. And also I'm a big believer, y'all know, in making sure you understand what's really behind it all, right? And that's this stuff back here of the accumulation property and the boundary and the associated notion of density. Okay. All right, so let's talk about some physics applications or physics examples anyway. I've got, what is it, 3 or 4 of them, I forgot. So I'm going to start off with a light bulb. This is my favorite example because I think it's so relatable. And I think y'all know how a light bulb works approximately. I mean, at least in the very broad strokes, right? Maybe not the specifics of the chemistry and the what's going on inside of the filaments or the LEDs, and that's something else. But the point is, light bulbs work by shooting out particles called photons, right? The filament at the middle, I'm going to keep saying filament, right? Because I'm stuck in the past. LEDs don't have a filament. But anyway, the shiny part in the middle, right, is just shooting out photons. It's like a water out of a spigot or something, right? But it's making these photons. It's generating the photon. Those photons weren't there, and then the little hot spot in the middle makes the photons and then throws them out every which way in every direction. Okay, and so here's kind of a picture of what that looks like. Here's the hot spot in the middle, whatever kind it is, and then you've got these rays going outward. Okay, so well, that makes a flux, right? And so you can look on the boundary here. You can look on the glass part of the light bulb, and you can talk about the flux that goes through that boundary. Okay, well, where does that flux happen? Where's that flux coming from? It's not coming from the glass, right? The flux is coming from the bright spot. It's coming from in there, right? Does that make sense to everybody? So when I say, you can algebraically, you can think of boundary flux as coming from the interior. Okay, literally, in this case, it is physically, literally coming from the interior, right? And so I think this is a great model for how to think about boundary flux. Boundary flux, you can just always think of boundary flux as, look, well, there's some fluid moving around here, and yeah, sure, the flux is measured on the boundary, but it's coming from wherever it's being generated in the interior. Okay, so it's a nice metaphor. And then, of course, now the divergence is telling us how much of that is happening sort of locally. And this is something you can confirm with some detailed calculations that we don't have time for, sadly. But if you were to compute the divergence in, let's say here, along in here, you'd get 0. Again, I think this is pretty physically satisfying. I claim the divergence is 0 there because if you were to think about some little region in there, some little ball, photons are shooting into that region and then just shooting right back out, right? Just as many photons are going out as in. When you have a light source, photons don't start collecting over time and just sitting there. Nobody's hoarding photons in some inside of the light bulb, right? Every photon that goes in goes out. So there's no flux that's being created there. There's no flux sink happening there, right? That's just, there is no flux happening there because there's no filament there. Does that make sense? Okay, so where is all this flux coming from? Where is the giveaway of where all this boundary flux that we're measuring on the boundary surface, where is that coming? Well, it's coming from the hot spot. It's coming from the bright spot in here. And so now I've drawn this as if it's kind of a point, and of course, physically it's not. Physically, a filament or an LED is a small, but not, it's got some actual volume. Right? It's a thing, however small, but it is a thing with some actual size. But that's where this tremendous amount of photons that are fluxing through the boundary, they're all coming from this teeny tiny little space. And so flux per unit volume, well, there's a lot of flux in not very much volume. And so your divergence there on the filament, inside the LED, whatever it is, the divergence is huge there. So that's divergence pointing at where the stuff is coming from. We good? Okay. All right. Now, there was an assumption that went into this example that is going to be different from the next example I'm going to show you. So, and that is that while photons are being physically generated, they're not collecting anywhere. So, the density is wherever you might happen to be looking. If you're talking about like right there, over time, the number of photons per unit volume in there, it's not changing. There's just as many photons going out as there are going in, and there's no collection of time collection of photons or time depletion of photons. They're being created, but they're not collecting. Okay. Or disappearing. So here's a different kind of a fluid example where we're going to make, in fact, sort of the exact opposite assumption. So this is a kind of a perspective shift, but it's just as physical, just in a different way. So here I'm going to talk about a gas. And the way you might think of this, what I'm going to encourage you to think about, imagine you've got a gas sitting there and it's, constant density or whatever. And then imagine you start to raise the temperature. And y'all may know the gas law. If you raise the temperature, then the volume increases, right? And if the volume increases, that means the density goes down. But it also means if you've got this much gas like this and the temperature goes up, then by the volume increasing, that means that the gas is actually therefore flowing outward. And so the fluid's flowing radially outward, kind of like this. As a result of the temperature increasing and therefore the density decreasing. Okay. So again, this is physically different than the last fluid example we were looking at. So here, there's no generation of gas. Up here, we're literally generating photons that were not there previously. Photons get generated and then they do stuff. Here, nothing's being created. Right. On the other hand, here the density is changing. How much gas there is in a given region, yeah, it's decreasing. I'm raising the temperature. The gas is expanding. The density is going down. Whereas up here, how many photons there are in that region? It's not changing at all. Right? Photon density is, nobody's collecting photons. Nobody's losing photons. Here we are literally losing gas in particular regions. So the interpretation of the divergence theorem here is a little bit different. So here's the divergence theorem. And you can take this vector field, pop it into there, compute divergence. Divergence ends up being, well, a constant. Right? And the interpretation I take of this is, okay, well, the flux here, that's representing fluid gas, right? Leaving the region. I've got fluid exiting the region. None was created to allow it to leave, right? So if you've got fluid leaving and nothing was created to replace it, well, that means that the density is decreasing, right? So, excuse me, the total mass is decreasing. So this flux is representing mass leaving the region, and therefore the total amount of mass in the region decreasing. Total quantity of mass going down. Divergence then, this divergence is measuring how much of that mass that's decreasing, how much is it going down in one place versus the other. And so you see this is a constant, and that's consistent with the density there, the mass per unit volume there is decreasing at the same rate as it is here, because in fact, remember our model is this is a gas where the temperature is going up and it's going up uniformly, and so yeah, the density is going down at the same rate. Yep.
Why did we say f of x is 3k? Could we also just say 5k?
Oh, no. It's literally if you were to take this vector field, right? That's so keep in mind this is kx comma ky comma kz, right? And if you straight up compute the divergence, it is literally that. Yep. Okay, so a different physical example, and I am out of time. So I tell you what, I'm going to just say we are going to kind of compare and contrast and generalize, and then also see some more physical examples next time. But the two examples that I have up here, I'm going to kind of unify next time. Okay, y'all have a good weekend. See you later. Have a good one. Okay, let's see here.